sub still. And I should put the identity. Oh, there's a math thing coming up. The Student Math League competition, Friday, March 3rd. Read this flyer if you're interested, and I will try to post something in D2L also about it.
Oh, is that like that pre-cal competition?
Yeah, and she's got prizes and things, and usually not too many people come, so it's easy to win a prize. Okay, so the identities, the trig identities, hopefully you've been figuring out that they're super important for trig sub. And the triangle that we use the most is this triangle here, the secant tangent triangle. And it's really important to be able to look at this triangle and write down all the different identities, or at least see them instantly. You should be able to look at a right triangle and do the Pythagorean theorem in your head. You should be able to look at that and say, oh yeah, secant squared is 1 plus tangent squared. Oh yeah, secant squared minus 1 is tangent squared. Secant squared minus tangent squared is 1. You should see all three of those identities instantly. And if you're not, you want to play with the Pythagorean theorem on those well enough so that you can see that. You should be seeing three identities. You should be seeing this squared plus this squared is this squared minus this squared is this squared minus this squared is that squared. So with all these Pythagorean identities, there's three ways to write them, moving things around. And we use that triangle quite a bit with trig sub. So keep that triangle close at hand, think about it, get fluent with it. Now let's go ahead and do another one of these. The only way to get good at trigonometric substitution is to do a bunch of practice. So with this one, we have a definite integral. And the definite integral with trig sub really adds kind of to the length of the problem, because you've got all this substitution at the end, and usually you're dealing with inverse trig functions. So when you see an indefinite integral with trig sub, you take a breath of relief, because you don't have to deal with the limits. But of course, this one has limits, so we've got to deal with them. And one thing that we always want to sort of think about is that if you have a difference of squares or a sum of squares, you want to go trig sub unless it happens to be set up in a way that U substitution would work. And when we look at this, it's important to understand why U sub does not work here. And U sub does not work because if we were to let U be that quantity inside the square root, if we were to let U be x squared minus 64, what's the derivative of x squared minus 64? 2x. And there is no 2x in there. So that's why U sub is not going to work, because the derivative of our U is not present anywhere in the integrand. Now there are some times, we saw one sneaky one where we had the square root of 1 plus the square root of x, where you could do some manipulation, but that's a rare case. If you don't see the derivative of the natural choice for U, U sub's probably not the right move. You know, there's a few oddball ones where you can do some manipulation and make it work, but most of them not. So, let's see. Okay, so we're going to use trig sub here. We see a difference of squares. X squared minus 64, that's a difference of squares. And the strategy that we are using is to create a difference of squares with a 1, either a leading one or a trailing one. It's going to make our life easier in the long run. And so what we're going to do is factor that 64 out so that we have a trailing 1 there. That's our strategy. And when that 64 is factored out to the front, first off, is it in the numerator or in the denominator? Denominator. So it's in the denominator now, so it has to stay in the denominator once we complete our factoring. The other piece of algebra that we have to remember is that the exponent that's attached to that 64 is what? The square root, which is an exponent of 1/2. So that has to come along, it has to stay attached to the 64. So that 64 has a power of 1/2 on it, so it's going to come out here as a 1/8. And then when we look inside the square root, we just have to do a little modification. So certainly that part will be -1. And then we have to modify this front term here. There's no 64 there, so we can think of it in two different ways. A very natural way is to think about putting a 64 in there so that you have a common factor to factor out to the front. But if you put a 64 in front of the x squared so that you can factor it out, you also have to put a 64 in the denominator so that you preserve the equality. So what we're left with is x squared over 64. And if you go backwards, if you take this 8 and you shove it back in the square root, you should get back to where you started. And when you push the 8 into the square root, it will go back into the square root as a 64. And so that 64 would cancel this 64 and make that one a 64. So you should be able to just double check that what you factored out gives you back what you started with. And now our last step in our algebra prep, and many of you will do this in just one step. You won't write this step down. It starts to become pretty obvious as you do more and more of them. We want to write this as a difference of squares. And this left term is not written as a square. Now it's written as a square. Now we've written it as the difference of squares. And we have a difference of squares with a trailing 1. That's how we'll refer to that. Bless you. And a difference of squares, your substitution is going to be sine or secant. Difference of squares, sine or secant. We only have 3 substitutions with trig sub: sine, secant, or tangent. Those are the only 3 we ever use. Tangents with the plus. Sine or secant if there's a difference. And so here's what we have to ask ourselves. Should that be sine or secant? And we look at our triangle over here, and we see that, oh yeah, secant squared minus 1 is tangent squared. That is an identity. Sine squared minus 1 is not an identity. 1 minus sine squared is an identity, but sine squared minus 1, not. I mean, you could force it to be an identity. You could say, well, wait a minute. Can't we force it to be an identity? Yeah, you could. So if you have this triangle right there, and you want to do 1 minus sine squared, what would that be equal to?
Cosine squared.
What kind of cosine squared? Negative. So 1 minus sine squared is positive cosine squared. But if we did sine squared minus 1, which is actually the order I meant to do it in. So sine squared minus 1, because we have a sine, this is in front. So if we did this one, what would that be? I think I heard it. Negative cosine squared. And can you take the square root of negative cosine squared? No. So this is not what we're looking for. We're looking for secant squared minus 1 because that can be replaced with tangent squared. Okay, so that is our clue. If we're going to let x divided by 8 be secant of theta. And we can make any substitution we want. The question is it going to be effective or not? And so if we want to make this substitution, we can do it. We just have to make sure that we replace all the x's and all the dx's with thetas and d thetas. So that would be the substitution. And so again, it just so happens that if you have differences in sums of squares, trig sub works very, very well. And sums and differences of squares show up a lot. All right, so let's get through all this substitution business. We have a dx in the numerator. So we come down to this and we isolate dx. So dx will be 8 secant tangent times d theta. So there is dx. Thank you. And then in the denominator, we have the square root of the x divided by 8 is a secant, so we end up with secant squared minus 1. And our limits of integration have changed. These are now theta limits. We're not going to find the theta limits. We're going to wait to the very end.
Where did the 8 come from for the secant?
That 8 right there?
Yeah.
So down here, if you solve for dx, you multiply both sides by 8.
Oh.
So we're replacing that dx. So dx will be 8 secant times tangent. And in the denominator, we have secant squared minus 1. Secant squared minus 1 is tangent squared. And the square root of tangent squared is tangent. So we can just wipe this stuff out right here. We have a tangent in the numerator, and that's going to wipe out the entire denominator. Turn them both into 1s. Secant squared minus 1 is tan squared. Square root of tan squared is tan. Those cancel. And we also have the 8's canceling. Voila, this one is not as bad as it looked. So there is our simplified integral. Integral of secant is? We start to remember that one just because we see it a lot. That's the natural log, absolute value of secant plus tangent. So every trig function other than sine and cosine, antiderivative will be some sort of log. This is the one we see the most, integral of secant. The derivative of secant is secant times tangent, and so that gives you a nice clue as to what's going to go in there. Instead of secant times, it's secant plus. But thinking about the derivative of secant is a good mental way to remember what goes inside the log. Now we need to create a portal that takes us back from thetas to x's. We've got to create a way to get back to x from theta. And this little triangle is going to be our portal. It'll take us all the way back to x. So we create this triangle same way every single time we create a right triangle that looks like you're sitting in quadrant 1 of a unit circle or quadrant 1 of the coordinate plane, however you want to think about it. Always build it that way. And the way we build this triangle is by looking up here at our let statement. So we are letting x divided by 8 equal secant of theta. Secant we know is hypotenuse over adjacent. So those are the two sides that we know. And every time we do trig sub, we know two sides of that right triangle instantly. Because we're letting sine of theta, tangent of theta, or secant of theta equal something. So we always are going to know two sides of that triangle. And then we have to figure out our third side. And that third side will be hypotenuse squared minus side squared. Exactly. Inside the square root. Hypotenuse squared minus side squared. And that should pretty much match what's up in here. Sometimes the exponent up here is a 3/2, but you should get whatever's inside that root right there should match very, very closely. Maybe not exactly, but very closely. And now we're capable of going back to x. So we come in here, secant of theta, we know right there is x divided by 8. Tangent of theta, we look at our triangle. Tangent is rise over run. Now we're back in the x domain. So our limits of integration, we can jump back to x limits. So 8 root 2 and 16. Those will return. After a little detour into the theta domain, now we have to do the inverse. Oh, not here. There's no inverses in this case. A lot of times there are. Okay, so let's get over here. We're going to plug in the 16 first. So natural log, absolute value, 16 over 8 is 2, plus, plug in 16 here, 16 squared is 256. 256 minus 64, I believe is 192. And then we still have the 8. And you know what I'm thinking is that maybe we shouldn't simplify this first term here. Maybe we should leave that as 16 over 8 because that 192 is not a perfect square, so there's no simplification that can happen here. So it might be useful to just keep that common denominator so that we can simplify later. The 192 is not a perfect square, so there's nothing we can do there. And then we're going to subtract off natural log. We'll plug in the 8 root 2. And again, let's just leave that denominator alone for now. Looks like we're going to have a bunch of 8s in the denominators. Now we have to square 8 root 2. So if we're squaring 8 root 2, we square the 8 and get 64. We square the root 2 and get 2. So we're going to have 128. 128 minus 64 is 64. Square root of 64 is 8. So we're going to end up with 8 over 8. And this should remind us of a really important log property. Division, exactly. So our log property that we're going to refer to here, we know that the log of A over B is the log of A minus the log of B. But we're going to go backwards because right here we have the log of this minus the log of that. So we have the right side, so we're going to turn that into division. So this will be the log of that in the numerator, so 16 plus root 192 all divided by 8. And all that's going to be divided by this one, which is 8 root 2 plus 8 all divided by 8. And there's an absolute value here. Do we need the absolute value at this stage? It's all positive, right? So if it's all positive anyway, you don't need it. Now the 8s cancel. The denominator 8, so we'll have 16 plus square root 192 divided by 8 root 2 plus 8. And again, we don't need the absolute value, so let's pop that off. We'll just put parentheses. And that'll be our final answer. Bless you. All right. Questions on any of our steps, any of the simplification, our cool triangle?
Could you also write root 192 as 8 root 3 and then pull an 8 out of everything?
Let's see.
Top
Oh,
and bottom?
does 8 go into 192?
8.
Oh, it
8
does.
root 3.
Oh, I was thinking,
64.
when I looked at it, I realized 4 didn't go into it, so I kind of just stopped looking. But you're right. This becomes 8 goes into there 2 times, and then we have a 32, so 84 times. Whoops. Wait, what did I just say? 8 times 24?
192 over 3 is 64, and root 64 is 8. So it'd be 3
Gotcha.
times 64.
So is this right here, 24 times 8, is that right? 32, 16, 17, 19. So then this, and like that is a perfect square in there of 4, so I think that's what you were saying, 32 root 6?
Add a root 3.
Oh yeah, this, oh you have a 3, let's
190
see, 24 is 6 times 4, so it should be that. So we could write it, that would be the simplest way we could write it, I believe. Did I write that right?
No, because your 8 would still be under the square root at this point, I think, right?
I don't know. I can't think right now. Do we agree on this? Is this 8 times? Oh, I didn't even put a square root up there. Yeah,
Yeah.
hold on. So this is there. This we agree with, and this we agree with. So that means the square root of 192 is going to be. Oh gosh, I can't do this. I can't even think right now. Oh my gosh. Tell me again. 192 is 64 times
3.
3. Thank you. So let's not do this. 64 times 3. So the square root of that is 8 root 3. That's what you said.
Yes.
Okay, thank you. Oh my gosh. It's not even Monday. So that right in there we can simplify. Okay. That is a great call. So this is 8 square root of 3. Because I convinced myself right there. 192 is 64 times 3. 12. Yeah. Wow. And so then we can simply cancel out an 8. Yeah, nice call, thanks. 2 plus root 3 over root 2 plus 1. There we go. Yeah, it felt like it should be simple. It should simplify, and I just couldn't see it. Yeah. Should have asked Siri. Siri is the best factor around. All you have to do is say, hey Siri, what are the prime factors of 192? But I don't have my phone. Okay, any other questions on any of the steps? Sure. So the triangle is always going to be a visual of whatever this is. So whatever your original substitution step is. That's how we build our triangle. So it's always going to be a sine, secant, or tangent equals some ratio. And so sine, secant, or tangent equal to this ratio allows us to build it. And we know that secant is hypotenuse over adjacent. Hypotenuse over adjacent. So hypotenuse over adjacent has to be x over 8, so the natural thing to do is to put x on the hypotenuse and put 8 as the adjacent side. And then we fill in the unknowns, so there will always be one unknown side. We use the Pythagorean theorem to fill in that one unknown side. And then that triangle will let us convert all these theta expressions back to x's. Any other step there you're not sure about? All right, let's go to our last couple here. So back a while ago, I'm trying to remember what the section number was. I can't remember exactly. But we've done some completing the square in the past. The completing the square that we're going to see here is going to lend itself to trig sub instead of just regular u sub. So let's take a look at what happens here. So we have this quadratic in the denominator. U sub is not going to work because the derivative of the denominator is 2x minus 6, which is nowhere to be found. So u sub's not going to work. If the derivative of u is not in there somewhere, not going to work. So we're going to complete the square. Can't use u sub. So we complete the square here. And remember that when we complete the square, we take the coefficient of x, bless you, divide it by 2 and square it. When we divide -6 by 2, we get -3. When we square it, we get 9. So we need a 9 to complete this, to make a perfect square trinomial here, to complete the square. So we're going to make this x squared minus 6x plus 9. So the simplest thing is to think about just grabbing 9 from the 34. We're going to take 9 away from the 34. This will be a 25. So now we've completed the square. We can factor. And when we factor, we will have x minus 3 quantity squared plus 25. Question?
Mary, how did you get the bottom for the moment?
How did I get this denominator? Completing the square, which is done by taking the coefficient of x, dividing by 2, and squaring. 6 divided by 2 is 3. 3 squared is 9. So we're going to borrow 9 from that 34. We're going to separate the 34 into a 9 plus 25. And now we see a sum of squares. So I want to show you 2 different ways to think about this. In both cases, it will be strategically helpful to make it a sum of squares with a 1. So I'm going to factor out the 25. So this is going to come to the front. There's no power on it. There's no square root. There's no square. So it's just going to come all the way out as a 25. And we're going to be replacing it with a plus 1. Now, when that 25, when we look right here and we say, oh gosh, there's no 25 here, you can think of this as 25 over 25. So then the 25 that's factoring to the front is that 25. So when we rewrite this first term in the denominator as a square, what will it be? Correct. So now we have a sum of squares in the denominator with a 1, with a trailing 1. And now it's set up for one of 2 things. So it's definitely set up for trigonometric substitution. Sine, secant, or tangent. Tangent, because it's a plus. And let's just go through this with trig sub, and then I'm going to show you something that maybe some of you see, maybe some of you don't. Let's just suppose we're going to do trig sub, though. So we're going to do x minus 3 divided by 5. We're going to let that be tangent of theta, because tan squared plus 1 is an identity. Tan squared plus 1 is secant squared. So we differentiate both sides. Dx on the left, d theta on the right. We're going to notice something really interesting here. Let's do our substitution. So we'll have 1/25th integral dx. We come down here, multiply both sides by 5, so dx will be 5 secant squared times d theta. Denominator becomes tan squared plus 1, which is going to be secant squared. So this secant squared and the whole denominator becomes secant squared. Tan squared plus 1 is secant squared. So we have a secant squared in the top, secant squared in the bottom. They both cancel. This gives us 1 over 5 integral of d theta. That seems awfully suspicious. So we integrate d theta, and we get theta. And you're like, is this really trig sub? This just seems way too unusual. Come back up here to solve for theta, inverse tangent of both sides, and that's the answer. What the heck? Gotta get it strong. All right, so that is the answer. If you come to a place like this, it means you missed a shortcut, or you missed something that you could have done without going through these extra steps of trig sub. The nice thing about trig sub is that if you forget that your inverse tangent, remember your basic inverse tangent. Your basic inverse tangent is dx over x squared plus 1. That's arctan. And you look here and you're like, oh gosh, it's already in arctangent form, right? That is arctangent form. It's just that instead of an x, we have this. So we could have actually gone straight from this form to here. We would have 1/25th times the arctangent of x minus 3 over 5, but then we would have to do RCR. The derivative in here is 1/5. Dividing by 1/5 is multiplying by 5. 5 over 25 would give us the 1/5. So the nice thing about trig sub is it takes care of, if you just happen to forget, a direct inverse tangent or a direct inverse sine. If you use trig sub with tan or trig sub with sine, it'll just come out anyway. Doesn't matter. So that's kind of cool. Any questions on, does everybody see that we could have gone straight from there to there? Should we do one other variation of this just to make sure that, so for example, let's clean one up a little bit. Let's suppose we have just this. Let's suppose we have dx over 2x minus 1 divided by, let's put another number that we haven't used yet today, that. If you have that, you can integrate it instantly. That's in arctangent form. The ones that we're forced to use trig sub for, there would be some other ornaments here. There would be, like this to the 3/2, or, some other thing, or just maybe a big square root, like that. We definitely have to use trig sub. That's not immediate. But this is instant. This is arctangent of whatever is in the parentheses here, so 2x minus 1 over 7. But then what is the RCR part? What would we do for RCR? Multiply by 7/2. We look in here. The derivative is 2/7. So you divide by 2/7, which means multiply by 7/2. So if it's in arctangent form versus trig sub form, you can cut right to the chase. But again, if you just didn't notice it because it looked a little more complicated than a basic inverse tangent, if you did your trigonometric substitution, you're going to end up right there. And it will work out just fine. So that's kind of nice. All right, question. Elijah, any question? Or?
No, I got it.
Got it? All right. Let's take a look at another completing the square. So with this denominator, the first thing I'm noticing is that we have a common factor of 2. And it's always a good thing to get rid of any common factor. Moreover, if we were going to complete the square, it's going to be a heck of a lot easier if we have a leading coefficient of 1. So we're going to do that. And everyone remember that nuance with completing the square? The square term has to have a coefficient of 1. So when you're back when you were doing the ellipses and hyperbolas, if the coefficient of the square term was not 1, you had to factor it to the front before you did the divide by 2 and square business. So you have to have a leading coefficient of positive of 1. And then when we go to do our completing the square here, we take, again, the coefficient of the linear term, right there. Coefficient, divide by 2 and square it. We're going to get a 9. So we're going to borrow 9 from the 18. So we have that. Now that trinomial right here is a perfect square trinomial. That's what completing the square does. It creates a perfect square trinomial. It creates something that's going to factor into a quantity squared, which is a perfect square trinomial. So this will be u minus 3 squared plus 9. We'll factor out the 9. So we will end up with a 1/18 out in front, factoring out the 9. And when we factor out the 9, let's do it one step this time. We're factoring out the 9, so this and this come out and mash with the 2 to make an 18. And we want to write this leading term here as a square, as a quantity that's squared, so we're going to write it as u minus 3 over 3, quantity squared. And is that, do we need trig sub here, or is it in arctan form right away? And it's in arctan form right away because we don't have any any monster brackets with a 3/2 or a power on it. It's all by itself down there. It's a denominator that's in this form. Sum of squares with a 1. So we can cut right to the chase. We are done. We know that we're going to get a 1/18. I'm going to leave a little space for RCR. We're going to have arctan of whatever's in the parens. Always a constant of integration. And then what's going to go in our RCR slot? So we're going to divide by 1/3. So we're going to multiply by 3. So the derivative here is 1/3. RCR says divide by the derivative, divide by 1/3. That's going to be equivalent to multiplying by 3. And then we just have a little bit of simplification here. 3 into 3 once, 3 into 18 6 times. Let's do, let me put another example up here. We haven't done with inverse sine yet. Let's suppose we have something like this. And we know that with inverse sine, if we're going to integrate and have an inverse sine form, it's going to be a 1 minus something squared inside square root. So if we have something like this, let's make this 4x divided by 9 quantity squared. That right there is in inverse sine form. We don't need to do trig sub here. You could, and it will work out exactly like the other one did. You'll get an integral of d theta, and it's going to pan out exactly the same. But if this is in arctan form right away, we can cut to the chase. So we know that this is arcsine form right here. So that's arcsine form. It's already in arcsine form. It's just that we have an RCR. So this is going to be, let's leave a little space in front. So we have inverse sine of whatever's in the parentheses, 4x divided by 9, integration constant. And what's the multiplier going to be out in front? 9/4, right? The derivative of what's in here is 4/9. Dividing by 4/9 means multiplying by 9/4. So having those two on recall is very helpful for the arctan and the arcsine. Now again, if you didn't notice it, it would all come out in the wash, no problem. If we said, oh, this is going to be an inverse sine, we're going to let 4x over 9 be sine of theta. This will lead us down to a place where you're going to get an integral of d theta. So as soon as you get an integral of d theta, you're thinking, oh gosh, I missed something. Yeah?
Go back up to the
Sure.
tangent.
Yeah. This far? Further?
Yeah.
Okay, so on your note cards, make sure you have those inverse sine, inverse tangent ones, because those are going to show up a lot. You can have a note card in your pocket, but you can't use it.
Why did you say that?
Just at night. Don't you do note cards at night? How do you go to sleep at night? You should be doing it. In this class, there's so many things you have to know that I would be having note cards every night to go to sleep. Unless you already know all those identities. If you know all those identities, you want the only way to sort of ingrain those things is to practice. Practice it. And it's a great way to get good night's sleep. Right? it'll knock you out fast. No, I promise it won't. I've experimented with this. It gives you good dreams. It gives you good dreams. Good dreams. There's nothing more satisfying than, just getting the right answer. Go through a trig subproblem all the way, and you get the right answer. It's just great. Yeah, it's like skiing the steeps. Okay, let's see. So let's go ahead and talk about our next integration technique. So this is called PFD, partial fraction decomposition. PFD. And this is a technique that you actually will see quite a bit in some other classes. Some of these other techniques are going to be more specific to Calc 2. PFD tends to be one that you see in differential equations a fair amount. So this is a good one. And it's not a hard one. It's probably the easiest of all these new techniques that you're learning. It really is just kind of an algebra-based thing. So what you've done in algebra a bazillion times has been to combine fractions. You've got these two functions over here. You get a common denominator, and you go this direction. So this you've done a million times, where you get a common denominator, and you add them together. What you haven't done is gone the other direction. The other direction. So in other words, how do we take this rational function and bust it apart into these partial fractions? How do we break that into fractions? Because think about integration for a minute. If you see an integration symbol on this, that's hard. But you look here, oh, that's easy. Right? That integrates immediately. What do both of these integrate to? Natural logs, right? Both of these are going to be natural logs. This will be absolute of x minus 2, and this is going to be 2 times natural log absolute of x plus 4 plus c. Right? So that's way easier to integrate those partial fractions than it is to integrate this. So if we could take our rational expression, a rational function here, if we could break it apart into these little fractions, it makes the integration much easier. And yeah, we could do more here, right? You could use a log property here and make this the log of x minus 2. I saw a couple of you looking at this like you wanted to do more math. Do you agree that that's how we would rewrite it if we use the log property? We can't combine the addition until this exponent, until this 2 is a coefficient, flies out of the way and becomes an exponent. So it would fly up here as an exponent. And then you could use the log of a product rule. The log of a product says if we have the log of a times b, that's going to be the log of a multiplied by the log of b. Plus right there. Plus. And so we're just going backwards. If we have a sum of 2 logs, we can turn it into the log of a product. So we have a log plus a log, so we can turn it into the log of a product. Okay, so this is called the method of partial fraction decomposition, PFD. So let's figure out how to do it. So first of all, what I want you to notice is that this denominator, and this is going to be a clue as to when you can use PFD and when you can't. Doesn't that denominator factor into x plus 4 and x minus 2? So the idea with PFD is that if you have a quadratic that factors, instead of completing the square and using trig sub, if you can do PFD, PFD is going to be a lot easier. Notice that the two fractions that get generated have an x plus 4 in one denominator and x minus 2 in the other denominator. So we've got these two factors in the denominator. We're breaking it apart. We're decomposing this one fraction into two fractions where one has a denominator of that and the other has a denominator of that. Okay, so that's going to be kind of the clue that PFD is going to be a good strategy if the denominator factors. So let's go ahead and try. Wow. Let's ignore that. So if we look here, we have two factors. And what this big horrible box is telling us is that if we can take our fraction and we can factor it so that here's the denominator, q is the denominator, and what it's saying, it's trying to generalize it, right? Math boxes always try to generalize things and make it as general as possible. We only have two factors here. So all they're saying is that if the denominator factors into a bunch of linear factors, does everyone remember the fundamental theorem of algebra? Any polynomial can be factored into a product of linear and irreducible quadratic factors. If you have a polynomial that has integer coefficients, no, they don't have it here, but if you have a polynomial with regular coefficients, integer coefficients, you can always factor it down into linears and irreducible quadratics. Does everyone remember what an irreducible quadratic is? A quadratic that you can't factor with integers. You'd have to use imaginary numbers. Can't factor it. So something like this is an irreducible quadratic, because you'd have to use imaginary numbers to factor it. So the classic irreducible quadratics, usually you see them as sums of squares. So that's not factorable. This you would have to use imaginary numbers and go x minus I and x plus I, and that's not where we're going. We don't want to deal with the I. We don't want to deal with imaginaries. So this is called an irreducible quadratic. So the fundamental theorem of algebra says if you've got a polynomial with real coefficients, you can always factor it into a bunch of linears and irreducible quadratics. So we know that it's possible to get down to have no cubes. We can get all the way down to linears and irreducible quadratics. So all this is saying here is that if we do have a setup where all we have are linears, the numerators are going to be constants. So if we look back at this prior slide for a minute, so here both of these are linear. So we're going to have denominator, one denominator for each, and then the numerators are going to be constants. Anytime we have a linear factor in the denominator, the coefficient in the numerator is going to be a constant. So that's all they're saying. So here we are going to say, okay, this fraction, this rational function is this. And what that theorem up there says is that we're going to break it into two partial fractions. Each will have a constant in the numerator. It's going to look like that. That is the partial fraction decomposition. Partial fraction decomposition will put a constant in the numerator for each one of those factors. And now we just go back to algebra and solve for a and b. So we're going to, in order to solve this with algebra, what we're going to do is clear the fractions. So we're going to multiply both sides by the denominator on the right so that we clear the fractions. So we're going to multiply this side by x minus 2 times x plus 6. Then those will cancel. Multiply this side by x minus 2 times x plus 6. So first step is to clear the fractions. Clearing the fractions will give us this. And as you do more and more of these, you will probably get to the point where you just write this second step down without everything I wrote in red. Because you're going to multiply both sides by this denominator every single time. So the left side's always going to become just the numerator. And when you multiply the denominator on the left by the right, do you see that you have some cancellation? This has to be multiplied by each fraction. When that quantity is multiplied by this first fraction, the x minus 2 cancels. So you're left with a times x plus 6. When you multiply by the second fraction, the x plus 6's cancel, and you're left with x minus 2. So we've got that. So as you do more and more of them, a lot of times you'll be able to just write that second step right down. And you just sort of notice, when this comes over to the other side, it has to be multiplied by both. X minus 2's cancel with that one. X plus 6's cancel with that one. So you get this linear equation. All right. Let's expand this. So if we expand this, it's going to look like this. And I'm just going to rewrite the right-hand side for a moment. I'm going to group the like terms together. I'm going to group the two terms that have an x, and I'll factor the x out. And then I'll group the two constant terms over to the right. So does everybody see that we could do that? We can take the two terms that have an x, we could pair them together, and we could factor out the x. And then we could just group the constants together, the terms that have no x or constants. Okay. Now, let me ask you a question. If you have two polynomials that are set equal to each other, let's do it on the board, actually. So what if, so this is an if. So if you have 2x minus 1 equals a, let's make it even simpler, ax plus b, what does a have to be? 2. What does b have to be? -1, right? The only way that two polynomials can be equal is if the corresponding coefficients match. It's the only way. If you have two polynomials that are equal, the coefficient of x has to match the coefficient of x. The constant has to match the constant. If you have a quadratic, coefficient of x squared has to match the coefficient of x squared. Coefficient of x has to match the coefficient of x. Constant has to match the constant. It's the only way two can be equal. I claim that's what we're dealing with here. On the left, what is the coefficient of x? 0. This is 0x plus 8. That's a polynomial. This is a polynomial on the right. The coefficient of x here must match the coefficient of x here. The constant here must match the constant there. So all we're doing is setting a polynomial equal to a polynomial and matching the corresponding coefficients. That's how we're going to build our system that will solve for a and b. So here is our system then. So this tells us that 0 is equal to a plus b, and 8 is equal to 6a minus 2b. So this is called the traditional method. This is the traditional method to solve for a and b with this system. We could divide a 2 out. So this is just back to college algebra. We're just trying to solve this system, and you all know how to solve systems. You either use the elimination method. I'm dividing by 2 here. Or what's the other method? Elimination or substitution. Right? Those are our two techniques to solve for a system of equations. So this is a linear system. We can use either technique. In this case, the elimination method works very well because when we add these two equations together, the b disappears. The b's cancel. So if we add the left side, we get 4. If we add the right side, we get 4a. So this tells us that a is equal to 1. And how do you think we get b once we have a? Plug it in. We can plug it into either equation. The easiest one would be the top equation. If you plug in that a equals 1 right there, b is going to be negative 1. So this gets plugged in up here, and that's going to tell us that b is equal to negative 1. So now we have our two coefficients. If you're a bigger fan of substitution and you don't like elimination, top equation, solve it for a, plug it into the second equation, solve for b, back substitute, and get a. So you can use substitution or elimination. This one right here is easy. Solve for a or solve for b, plug it in here, you get the same answers. So substitution or elimination. So what this tells us then is what the two partial fractions are. So our original integral, we can call it something. Let's call it omega. Why not? We like omega. So omega is then equal to the original integral. The original integral is now equal to 1 divided by x minus 2 and b is negative 1, so negative 1 divided by x, was it x plus 6? Yeah, x plus 6. So now we have our original integral omega. We've rewritten it like that. And that is cake. We know we can integrate each of these to a natural log absolute value of the denominator. Once we get to these linear denominators, we're golden. So we have that. And on an exam, 100% right there. You can stop there. You don't need to. I'm not going to require you to do log properties. Could you do log properties here? Of course. You can do the log properties here. But on the exam, it's completely fine to, and I'll say it right in the question, no need to combine with log properties at the end. But in the homework, a lot of times it wants you to do that. All right, let's look at that. Any part of that that you want to ask about? Yeah?
How did you get the omega? I'm confused.
How did we get this?
Yeah.
So what we're doing is taking the integrand, right there. We're taking the integrand and we're going to rewrite it as this. So the integrand, what's inside here, is going to be replaced with that. So then the process of solving for a and b allows us to figure out what each of those little fractions, those partial fractions, will look like. So we solve for a and get 1, we solve for b and get negative 1, and so that just allows us to rewrite the integrand as a sum of two partial fractions instead of as one more complicated fraction.
Okay.
So now we have two partial fractions. And the whole the strategy works beautifully because each of these partial fractions, if we have a linear denominator, it's instantaneous natural log as the antiderivative, which we've gotten very familiar with the antiderivative of 1 over x. Other questions on that? So again, this is called the traditional method. The traditional method equates two polynomials, and we set the corresponding coefficients equal to each other, and that's what builds this system. Coefficient of x, constant, constant. That's how we build our system. And then we'll do another method after we take a 10-minute break. That is called the convenient value method. And it is a very convenient method. That's a little faster than the traditional method. But there's times where we have to use the traditional method, so you can't just throw the traditional method out, even though we like to throw traditional things out. Method. This method is called the traditional method, where you equate the coefficients. And when we get to irreducible quadratic factors, you really have to do the traditional method. But there is a very slick shortcut with the situation that we have here, where we have two linear factors. If you have all linear factors in the denominator, this method that I'm about to show you is so much quicker. You still need to know how to do the traditional method for these other cases. But if it's all linears, check this method out. So let's get to this stage right here. So we're going to take that. Is it going to let me, can I copy that? I guess I have to do the right click thing. So let's take a look. We're at that stage right now. Again, I guess, and paste. Okay. So let's suppose we're right here. This piece right here, this equation, so the way we solved it was to expand it all out, and we equated the coefficients. This right here is an identity. In other words, this is true for all x. So that's true for all x. So this method is called the convenient value method. And these convenient values are going to be the zeros of the two factors. So if this is going to be true for every single x, in particular, it has to be true for x equals 2, and it has to be true for x equals -6. So the convenient value method, the shortcut is to pick the zeros of each factor and plug it into this identity. So notice, what are the two convenient values? X equals 2 and x equals -6. All right, well, if this is an identity, it's true for all x, we're just going to pick x equals 2. When we pick x equals 2, we end up with a times 8 plus 0. Divide by 8, we get a is 1. Very fast. When we plug in x equals -6, we're going to get 0 plus -8 times b. Divide by -8, and we get that b is equal to -1. So the convenient value method is super fast, but it only works if you have linear factors. So that all that work right there was to find a and b versus, all this system stuff. Much less labor if the convenient value method is an option. And it's an option if you have all linear factors. All right, so that's a side note. Let's take a look at this one. So the one thing that we have to remember is that our convenient values, that does not want me to turn it into a mouse. So that convenient value, so that method that we just did, the traditional and the convenient value method, both require the denominator to be factored. In order for us to predict what those fractions look like, right here, we needed to predict what these two fractions look like. We had to have the denominator in factored form. So that's going to be a first step. When we look at this, the denominator is not factored. So first step is that we have to put it in factored form, or we won't be able to predict what those partial fractions are. The first thing I notice is that there's a common factor of x that's going to come to the front, and then we're going to be left with x squared minus 1, difference of squares, x minus 1, x plus 1. So there is the factorization of the denominator. We see that there are 3 linear factors, so this tells us that we can take the integrand with these 3 linear factors in the denominator, and we are going to be able to rewrite that integrand as a sum of partial fractions with constant numerators over each of those individual denominators. So that is what our decomp is going to look like. We just ignore the numerator. Our total focus is on the denominator right now. And what we will have is that this is what when we multiply both sides by this denominator, this is going to be the polynomial on the left that we have to match coefficients with if we use the traditional method. So here comes the algebra step. We clear the fractions. So we imagine this denominator. It's got 3 factors. When we multiply it by each of these 3 fractions, 1 factor will cancel for each. When we multiply it by the a fraction, the x's cancel. So we're left with x minus 1 and x plus 1. When we multiply that denominator by the b fraction, the x minus 1's cancel. So we're left with b, x, and x plus 1. When we multiply it by the c, we'll be left with that. Any issues with that multiplication? We always do the same thing. We clear the fraction by multiplying both sides by that denominator. So that denominator gets multiplied by each of the 3 fractions. 1 factor cancels with each. So now, if we were going to do the traditional method, we would have to expand this whole side, FOIL there, distribute here, distribute there. But because these are linear, the convenient value method is going to apply. So the convenient value method what will be our 3 convenient values? So it's going to be the zeros of each of those factors. So it's going to be the x value that makes this 0, the x value that makes that 0, the x value that makes that 0. So it's going to be the zeros of those 3 denominators. Those are our convenient values. So now we just plug in the convenient values. And watch how slick this is. Plugging in 0 on the left gives -2. Plugging in 0 on the right, this is gone, and this is gone. If you plug in x equals 0, both of those are gone, and you're left with a multiplied by -1 multiplied by +1. So you get that a is 2. So if we have linear factors, this is definitely the move, convenient value method. Now we plug in -1. -1 on the left, -4 minus 2 is -6. -1 on the right, gone, gone. When we plug in -1 for x, -1 plus 1 in both these cases, both those are gone. So plugging in -1 over there, it's the only stuff that's left. That's going to be c times -1 times -2. So this is going to tell us that c is equal to -3. Now we plug in 1 across the board. 1 on the left, 4 minus 2 is 2. 1 on the right, gone. 1 minus 1 is 0. Gone. 1 minus 1 is 0. So we're plugging our 1 in just here. We're going to get b times 1 times 2. So we're going to end up with b is equal to 1. So that's a pretty slick, easy procedure if you have linear factors. You can at least envision how much more complicated it would be to do the traditional method. You'd have to FOIL this all out, then you'd have to distribute a, distribute bx to that, distribute cx to that, then you'd have to collect the square terms, collect the linear terms, collect the constants. It's going to be way more work. So now we can rewrite the original. Again, let's call it something. We'll say that it's omega, just because that's easy. So omega will equal integral of a divided by x plus, I can't remember which order I put them in, so b is over x minus 1 And then c is over x plus 1. So the original integral is broken apart into 3 partial fractions, each of which is immediately integrable using the log function. So we'll have 2 natural log absolute x plus natural log absolute x minus 1 plus, whoops, minus 3 natural log absolute x plus 1 plus c. And again, that's totally fine. You can just stop right there. We don't need to use log properties. It's going to get too tedious to always use log properties. We do enough algebra. All right, any steps there that you're curious about, not sure about? All right. So, question?
I'm just confused why. Can you go over omega again?
Oh, we're just calling omega the original integral. Instead of rewriting the whole original integral again, we're just calling it omega. We just need to call it something. Books will usually call it I. But I is boring. Right? Call it I. Call it omega. Okay. So I'm going to set this one up and then let you work it out. So notice this is going to be a slight amping up of what we just did. We still have linear factors, but notice that we have repeated linear factors. And this big box here is saying what you do with a repeated factor. So they're saying, well, what if the power on your linear factor was m? Well, then you're going to have m partial fractions. You're going to have a partial fraction for every power of the repeated factor. So for example, here's how our setup is going to go here. We're going to take the inside, we're going to take our integrand, and this is how it is going to look. So we are going to break it apart into a over x minus 6 plus b over x plus 2 plus c over x plus 2 squared. So this factor is repeated right there. And we have to have a partial fraction for each power. All right, so you guys take it from here. So clear the fraction first and get your equation. Let me know if you need help clearing the fraction or setting up that equation. So the first really important step is to get to that equation and clear out the fraction. So because this is repeated, so this is saying up here, if it's repeated, you have to have a fraction for it raised to the first power, a fraction for it raised to the second power, that's 7, or whatever that is. So here, our m is 2. So that means we have to have a fraction for x plus 2 is 1, and a fraction for x plus 2 is 2. So we have to have a fraction for each power, all the way up here. So if this was x plus 2 to the 4, we'd have b over x plus 2, c over x plus 2 squared, d over x plus 2 cubed, e over x plus 2. Back, yeah. Yeah, but even if you wrote it like this, right, don't you have 3? You're going to end up with 3. You're going to always end up with this. Yeah, that extra power. Because if you wrote this as b over x plus 2 and then c over x plus 2, those would be the same. And we need to build up to a square. we have to get squared here. If you wrote this as b over x plus 2 and c over x plus 2, that would not build up your space. You've got to somehow get squared there. So create this. The way we create the square is kind of a partial fraction for each power
That was my
of that
problem,
repeated factor.
because I just plugged things in and they did not come out with it.
Yeah, of course. Questions?
This doesn't have a cancel out of it. That cancels that. So that is there.
So, if you're trying, so remember that we're trying to get up to this term here that has this factor that has a square. If this didn't have a square over here, there's no way to get to a square there. There's no way to build it up. So the only way we can get to a square term is if we start with a square.
You see what I mean?
So, go ahead. Then you have a common denominator of x plus 2, so you would never have to get a square. Right. So the idea with the repeated factor is that you have to have, whatever the highest power, like if that was a 4, you would end up having to have something with the fourth power there as a mechanism to get built up to the fourth power.
And now that's a zero. Or one has to go after, so you plug in x or zero.
So if it was a 4, if this was a 4 here, we'd have an x plus 2 to the 1, an x plus 2 to the 2, an x plus 2 to the 3, and an x plus 2 to the 4. So we have to have a partial fraction for each power. So if that power started out as a 4, we'd end up with 4 fractions. See, oh, that one. Let's see, so that equation looks good. And you're plugging in your convenient value of negative 2. So on this side, you're going to get 64. Negative 2. Something's wrong here. When you multiply by this denominator, you're just going to have an x plus 2 squared here, not an extra x plus 2. Because when this multiplies by that, the x minus 6's cancel. You'll be left with that one. When this multiplies here, you're going to end up with just one x plus 2 in the top. And when you multiply this by this one, you have no x plus 2's left. Because that one's to a 2, that one's to a 2, so the only thing left is that. You see it? Yeah. All right, let's go through creating the equation. So the multiplication is multiply both sides by this denominator on the left. So that denominator has to get distributed to each fraction. So you're multiplying each of these fractions by that denominator. So when you look at this first fraction, the x minus 6 and the x minus 6, those are going to cancel. Right? That's the common factor between numerator and denominator for the first one. So we're going to be left with 16x squared equals, the x minus 6's cancel, so you'll have a times x plus 2 squared. And then with the b fraction, the x plus 2 in the denominator will cancel with one of the x plus 2's in the numerator. So you'll end up with a b, an x minus 6, and an x plus 2. And then when the denominator is multiplied by the third fraction, that's going to cancel with that. And the only thing left is the x minus 6. So you're going to have c multiplied by x minus 6. So plus c times x minus 6. So that is the equation. That's where we're going to generate our system if we go traditional method. That's where we're going to get our convenient values and plug them in if we go convenient value method. So any questions on generating this equation? So to get to that equation, we multiply both sides by the left denominator. And when you multiply the right-hand side by the denominator, you have to distribute it. So denominator by this, denominator by this, denominator by that. And this denominator, when we multiply it over here, it's up in the numerator. And when you multiply it over there, it's in the numerator. So it's canceling things from the denominator. Okay, so now let's go convenient values. There's only 2 though. And we have 3 coefficients. So we're going to have to be a little creative here. So our convenient values, tell me the 2 that we know for sure. -2 and 6. So let's go through those first. So we know these 2 convenient values. Plug in -2 all the way across. -2 on the left is going to give 64. 4 times 16. On the right, when we plug in -2, this is going to be gone, and that's going to be gone. -2 plus 2 is 0, so both of those are going to have terms that turn into 0. And the only one that doesn't is over here, and that's going to give us -8c. Divide by -8, and c will be -8. Okay. Now our next convenient value is 6. Plug it in on the left. I don't want to simplify this yet. I'm bad at math today. So we're going to leave it at 16 times 36 for now. And then on the right, when the 6 goes in, don't these 2 go away? So 6 minus 6 is 0 for both of those. So we plug in the 6 here, and we get 8 squared, which is 64a. Question?
So you got the x equals -2 from the b.
Yeah, -2 is the x value that makes this 0.
Right.
X equals 6 is the x value that makes that 0.
So when looking for the x's, you want to look at the original.
You can look here or in here. Yeah, either way. It's going to be the same either way.
So it doesn't matter, because like the one before, the example before had like the b went with like the b value and the a went with like the a value thing.
Yeah, you just want to look at the denominator. The convenient values will make the denominator 0. When you're finding your convenient values, it doesn't matter what a, b, and c are.
So like how did that like cancel the a and b out to just get c?
Right here?
Yeah.
Because you're multiplying this quantity right here. There's no a and b in here. You're multiplying this by that. And so you're multiplying right here by x minus 6 multiplied by x plus 2 squared. So you're multiplying these together. That's in the denominator, that's in the numerator. And that leaves you with the x minus 6.
So like the one that we don't know is b then, right?
Say that again, the one that we don't know.
Is b, like the x value for the b thing.
I mean, the 2x values that we know are -2 and 6.
Right.
They're
And
not
so-
associated with, I mean, here -2 is associated with b and c
Right.
because it causes both those denominators to be 0. So I wouldn't say that's just associated with b because it's also, I wouldn't associate it with any. I would just look here and say, this is 0 when x is 6, this is 0 when x is -2. So those are the 2 that you're going to use for sure.
So like how did you know that the x equals -2 would get a c value out of that?
Because if you plug in -2 here, this is gone.
Yeah.
If you plug in -2 right there, that's gone. This is the only one that doesn't disappear when you plug in -2 for x.
So you just have to plug it in like the whole thing?
Yep, the whole thing. All the way across, the whole thing. Yeah, yeah. Yeah, there's no shortcuts there. Plug it in for every x. And then, so what is this a going to give us? 9? Right? 16 divides into 64 4 times. 4 divides into 36 9 times. So there's 2 of our constants. We're missing one. One constant is missing. There is not another convenient value that causes all this zeroing out. Each of these convenient values zeroed out 2 of the terms. So that was convenient. Now, what we can do, there's 2 different strategies right now. We can just pick another convenient-ish value, or we could substitute these 2 that we know. We could plug in the c there, we could plug in the a there, and we could move stuff over and we could convert over to the traditional value method. So there's 2 ways to go here. My strategy, if we're still just dealing with linear factors, let's just pick another convenient-ish value. Doesn't matter what number we pick. We just pick a number that's convenient-ish. 0, that's convenient-ish. On the left side, we end up with a 0. That's usually pretty reasonable. You could also look over here and say, oh, if we plug in -1, then this is going to be a 1, and that's going to be a 1. That's pretty convenient, too. So it does not matter. You can pick any number you want. I would not pick an irrational number. Don't pick square root of 2. But pick an integer that's going to make at least something simplify pretty nicely. So if we plug in 0 across the board, here we're going to be left with 4a. Plug in 0 here and here. That's going to be -12b. Plug in 0 there. We have -6c. So that'll be our third equation. And that's how we can solve for b. So let's see. How are we going to solve for b exactly? We're coming up here. We're going to isolate the b. And I'm going to divide by 2 simultaneously. Let's divide by 2. So we're going to have 6b on the left. And on the right, we've divided by 2, so that becomes 2a minus 3c. And what do you think we're going to do next? We'll divide by 6. And we'll also plug in the 2 we know. Exactly. We know the a, we know the c. Let's plug those in. So b is going to be 2 times a. So that's 2 times 9 minus 3 times 8, -8. And then divide by 6. So that'll be b. Whatever that is. So we have 18 plus 24 divided by 6. 7. Sounds good. So that'll be our c. Our b. The b. That will be the b. Okay, so now we have all 3 of our coefficients. Let's call the original integral something. I'll just call it omega. So the original integral is now equal to, we're breaking it into 3 partial fractions. We solved for a and had 9, so it's 9 over x minus 6. And then b, which is 7, divided by x plus 2. And then for c, we had -8. So -8 over x plus 2 squared. dx. So that is an integrand that's way more integrable than that first gnarly fraction. I know you know the first 2. Those ones I know are not hanging you up in the least. I'm going to rewrite the last one in a suggestive way that hopefully will then lead you to not be hung up on that one. So if we have an x squared in the denominator, we can bounce it up to the numerator and change the exponent to negative. And then use the power rule. So then our final integral, so these 2 are going to come down. Then this will be, we have -8. We add 1 to the exponent. That's going to give us a -1. We divide by that new exponent. So add 1, divide. So we're going to have x plus 2 to the -1 divided by -1, and then plus c. So that'll be our final answer. You, of course, could write this as 8 divided by x plus 2 if you wanted to get rid of the negative exponent, which we frequently like to do, present our final answer without any negative exponents. All right, any step you're not sure about. All right, so you all start this one. We have another repeated linear factor. So do your setup, do your PFD with three. You're going to have three partial fractions. And you need to have a partial fraction for each power of that repeated factor. So you are going to have three. You will have three partial fractions. Let's see if you can build that one up. Well, this flyer is pretty cool. You can just scan this QR code and it brings you right to the information for this competition on March 3rd in this room from 10 to 11 a.m. Federico,
Yes.
are you going to be here for this?
Yes.
Yes, cool. Jesus, did you have a question? You know, I think I think I heard Debbie say that there's going to be like $25 gift cards and, you know, money.
How much?
$25. 25 bucks here and there. And you get put in for a drawing for like a ton of stuff. Like if you just come and do that, it doesn't matter. Your name automatically gets thrown into some drawing for like $1 million or something.
That's pretty crazy.
Maybe that was the wrong number of zeros. Something.
1 million fractional pennies.
1 million rupees. $1 million Bitcoin. All those opportunities we've missed out on. Let's see. So it's going to be, yeah, those are going to totally cancel. So it's just plus C. Correct. Correct.
And we're just getting 0.
Yeah, let's just get to the equation.
Yeah.
How many convenient values are you going to have? You're only going to have one true convenient value. So pick two others that are convenient-ish, that will simplify things, but not quite as nicely, but will simplify things. And I'll catch up to you all. Okay, so we've got our equation, and that's our equation that is either going to lead us towards convenient value method or lead us towards traditional method. There's only one true convenient value in the sense that there's only one that's going to cancel out two of the terms, and that's 2. When we plug in x equals 2, we get that c is going to be 4. The other two convenient-ish values I picked are 0 and 1, and it doesn't matter what you pick. Does not matter at all. 3 is a reasonable one because 3 minus 2 is 1. That's going to make these two simple. If you picked x equals 3, doesn't matter. So I picked x equals 0 to make the left 0. And now on the right with 0, that'll give 4a and negative 2b and plus c. And I picked 1 also. So negative 1 squared is 1, so that's an A. 1 minus 2 is negative 1, and then C. So that's where we're at. That's where I'm at. You might have slightly different equations, but it's not going to matter. So now we go back to our college algebra, solving systems. Substitution or elimination, both of those work totally fine. Does not matter which way you go. The first thing I notice is that we've got a C. We can plug our C in. So I'm going to rewrite the first and third equations by plugging in the C value that we know. So this equation here is going to be 4a minus 2b, right there, plus 4 equals 0. And this equation right here is going to be a minus b plus c, which is 4, equals 1. So plugging in the c that we already found into both of those equations. And the natural thing to do would be to put the constants on the right. So I'm just going to do that. I'm going to put the constants on the right. I'm going to subtract 4 to the right of this one, subtract 4 to the right of this one. So these are going to be the equations that I end up with. You can divide the top equation by 2, just to simplify it a little bit. And then substitute or eliminate. Does not matter. So these are the two equations that we are left with, and we just have to do whatever makes the most sense to us. I'm just going to subtract them, because I notice that if I subtract the second equation from the first equation, b will just disappear. So I'm going to subtract those two. So I'm going to take these two equations and I'm going to subtract. 2a minus a is a. Negative b minus minus b is negative b plus b, which is 0. Negative 2 minus a minus 3 is negative 2 plus 3, which is 1. If you wanted to substitute, you could substitute. Solve the bottom equation for A, plug it into the top equation. Solve the bottom equation for B, plug it into the top equation. Does not matter. You should end up with A is 1. Confirmation? You get A is 1? Good. Now we have C, we have A, and to get B, plug it into either of these equations. Plug A equals 1 in right there, subtract it, you get negative 4, so you're going to get B is equal to 4. So it will not matter what you picked for your second two equations here. These two, whatever you want, you'll end up with the same coefficients. Yeah? So if we plug in a equals 1 right there, we subtract that over, negative b is negative 4. Negative b will be negative 4, so positive b will be positive 4. Now we are poised to rewrite our original integral, whatever letter you want to call it. Let's just say that it's equal to an omega. So it's going to be a over a is 1 over x minus 2. B over x minus 2 squared. And then C over x minus 2 cubed. So C x minus 2 cubed. And all of those are pretty easy to integrate with the power rule, other than the first one. First one is log. The others are power rule. I'm just going to rewrite each of those. We'll do all of our integration all at once. So we just rewrite these so that they are in the numerator, and it'll be a heck of a lot easier. each of those can integrate. So for the second two, add 1, divide by the new exponent.
Can you go back up really quick?
Yes, absolutely. Further?
No, that's good.
Bless you. Could you get a different answer?
I got B was negative.
So right here, if this is the equation we're using, if we plug in A equals positive 1, if we subtract it over, we get negative B is negative 4.
Yeah, I see that there. I don't know how I ended up with negative 4.
Did you end up with positive 1 for A?
Yeah.
Let's see. And when you're yeah, did someone else get the same ABC?
I see what I did.
You see it?
Yeah.
-1. Trivial error. Sign error. Anyone have any questions about the integration steps? Add 1, divide. Add 1 to -2, divide. Add 1 to -3, divide. And if the coefficient of x was not 1, like it happens to be, we would have to do a little RCR. If this was a, right, if there was a 3 in the coefficient here, we'd also have to divide by 3. If there was a 5 coefficient there, we'd have to divide by 5. All right, so that is repeated factors. Now, the last possible scenario, the granddaddy, irreducible quadratic. An irreducible quadratic happens to Murgatroyd. So, if we have an irreducible quadratic, so remember, irreducible quadratic just means it doesn't factor over the real numbers. For us, usually, it's going to be something that we're going to see pretty easily has a b squared minus 4ac that's negative, so it needs an imaginary. Right? When you do the quadratic formula, b squared minus 4ac, if that's negative, you get an imaginary. But notice the big difference here is that if you have an irreducible quadratic in the denominator of one of your partial fractions, instead of the constant numerator, we have a linear numerator. So with the other ones, we had a linear factor in the denominator, like x plus 5, and we had a constant up top. Here we have a linear expression in the numerator. So the idea is that we want to create this fraction so that it's a proper fraction. So the power in the numerator is less, but we want it to be the most general polynomial in the numerator that still makes it a proper fraction. So if the denominator is a quadratic, the numerator can be up to a linear and still be proper. So that's going to be what we do. So here is our first example. We've got 2 factors in the denominator. That's a linear factor. And this is an irreducible quadratic. This is not factorable over the integers. If you wanted to test to prove it to yourself, you look at b squared minus 4ac. If that's negative, then you know you need imaginary numbers. So b squared is 4 minus 4, a is 1, c is 2. 4 minus 8 is negative. So that shows us that it's definitely not factorable over the integers. That means it's an irreducible quadratic. All right, so our process will be very similar to what we did before. We take the guts of the integral, we take the integrand, take it exactly as it is, factored, and it's going to be a divided by x plus. So that linear factor still gets a constant coefficient in the numerator. And the second fraction will be bx plus c. divided by this irreducible quadratic. So that's going to be our partial fraction decomposition step. And then we do what we did before. We clear the fractions.
So how did you know if it was gx plus c, or is that just like a...
It's always going to be a linear expression. We already used a, so we're going to use bx. If we put that one first, we could call it ax plus b and then c over x. So it's not going to matter if you have it out of different order to your partial fractions. So we just need it to be linear, and we usually pick the coefficients a, b, c, d, e, f. Hopefully we don't get to f. That's too many coefficients. Okay, so now we're going to clear the fractions. So now we're going to generate our PFD equation. Our PFD equation is going to be that equals a multiplied by the quadratic plus bx plus c multiplied by x. There is our PFD equation. The PFD equation, we have a couple of strategies here. We only have one convenient value. It is very, so we could just go traditional method right from the start. Or we could use a hybrid. We could use convenient value for the one convenient value and simplify it a little bit and then go traditional. Or we could go traditional from the start. It doesn't matter. Let's just go traditional from the start on this one and see how that plays out, because we haven't done one of those in a while. So if we're going to go traditional method, we have to distribute. You can, if you can kind of see it in your head and you don't need to write this all out, you could bypass this step. But let's write it out. So we have that. And now let me highlight coefficient of x squared, coefficient of x squared, coefficient of x squared. So we are going to have 1 as the coefficient of x squared on the left. On the right, we have a plus b. Then we'll go to the coefficient of x. That's a positive 3 on the left. On the left, positive 3. On the right, there's a coefficient of x. There's a coefficient of x. So we will have 3 equals 2a plus c. And then, need a different color up here. Let's grab that color. So on the left, we have a 2 for the constant. Come over here, the only constant term is right there, 2a. So we will have 2 equals, so left, and then over here it's just 2a. So right away we can isolate a, and we have that a is equal to 1. So we've got that right away. And so now we just have to figure out the other constants. We back substitute. We do whatever we need to do. What is b going to be if a is 1? 0. So now we've got 2 of them. Plug a in here, and we get that c is also equal to 1. So now we have all of them. 3 constants. So with irreducible quadratics, almost always you have to do at least part of it traditional method. You do it all traditional method, or you could try some hybrid approach. Traditional method works just fine. So we have omega, the original integral, we'll call it something. That's going to be equal to a divided by x. A was 1, so 1 over x. And then plus, oh, that's convenient, b is 0. So then we're going to get 1 over this thing. right. Any questions up to that step? We should all certainly agree that that integral is going to be easier than this one. We know how to integrate that right away, and that we actually have a technique for, which we'll use. So any issues up to that point? Good up to the integral part. All right, let's integrate. So, obviously the first one we don't have any trouble with. Second one, what's the strategy we'll use when we have a quadratic in the denominator that's not factorable? Say what? Did you say just erase stuff? Just use your eraser. Make it a convenient integral with your eraser.
Make it a negative exponent.
That's not going to work here because we've got this crazy business here with, so that does work if we have a linear denominator, we could pop it up top. If it's linear raised to a power, for sure. So we have this technique. We did it earlier today even, unless I'm remembering wrong. Please. Complete the square. Excellent. Thank you for that idea. I appreciate that. So this is going to be x squared plus 2x plus 1 plus 1. So the coefficient of x is 2. Divide by 2 and square, we get a 1. So we need to take a 1 away from that constant on the tail there. So we're going to rewrite this as natural log absolute x plus integral of dx over x plus 1 squared plus 1. And what is that?
Inverse tangent.
Tangent inverse. Tangent inverse. And we don't even have to do anything there. There's no RCR. It's just an immediate inverse tangent of x plus 1. And then integration constant. So PFD is, it's a procedure. It's not a crazy procedure. There's definitely algebra. You're going to have to refresh some of your algebra solving systems and whatnot. But nothing too nutty. So these two factors here are both irreducible quadratics. So these being irreducible quadratics, this is what we will be using for our PFD. We're going to have an y plus b over y squared plus 1. So we are going to need a partial fraction for each of the factors in the denominator. So that'll be our setup. Irreducible quadratic twice. And now we get our PFD equation. Our PFD equation we find by clearing all the fractions. We clear the fractions by multiplying both sides by the left-hand side's denominator. And here's what we'll end up with on the right. And if everything's an irreducible quadratic, you definitely don't want to be doing convenient values. You want to definitely just stick with traditional method, which means expand everything out and match the corresponding coefficients. So we really don't have any choice here. This is going to be ay cubed plus by squared. I'll write it in descending order, plus 2ay plus 2b. And then over here we'll have cy cubed plus dy squared plus cy plus b. So there is our PFD equation. I'm going to put in a little bit of space here. What is the coefficient of y cubed on the left? 0. So we have 0y cubed plus 0y squared plus 0y plus 1. So we can imagine those placeholders. That 1 on the left is still a polynomial. This is a polynomial on the left. That's a polynomial on the right. The only way those two polynomials can be equal is if the coefficients match. So on the left, the coefficient of y cubed is 0. Now let's come across to the other side. So there's 2 cubed terms on the right. So that tells us that 0, bless you, must be equal to a plus c. Now we go to the squares. The coefficient of the square on the left is 0. Coefficient of squares on the right. So there's a square, there's a square, there's a square. So it looks like 0 will be b plus d. And then let's go linear. Coefficient of y right there is 0. There's a coefficient of y, and there's a coefficient of y. So we're going to have 0 equals 2a plus c. And then we have to go to constants. So the constant on the left is 1. Coming across here, there's a constant, and there's a constant. So 2b plus d. 1 equals 2b plus d. All right, so there is our system to solve. And it's not too bad because we see that it's paired off pretty nicely. If we look at these two equations, equation 1 and equation 3, we could subtract those. I'm going to do equation 3 minus equation 1. And that is going to lead us to, so I'm doing 3 minus 1, 0 minus 0. On the left is 0. On the right, 2a minus a, that's a. C minus c is 0. So we get that a is 0. And if a is 0, c is 0. That's great. So we have 2 zeros. And then if we pair off equation 2 and equation 4, let's see. Let's do 4 minus 2. So if we do equation 4 minus equation 2, 1 minus 0 is 1. 2b minus 1b is 1b. d minus d is 0. And if b is 1, d is minus 1. So those will be our 4 coefficients. ay plus b. So a and c are 0. Oh, good. The coefficients of y are 0 in both cases. And b and d, 1 and negative 1. Okay, so we have 1 over y squared plus 1. And this is our original integral is equal to that. 1 over y squared plus 1 and negative 1 over y squared plus 2. First integral, yeah, that's an arctan right out of the gate. So that'll be arctangent of y right out of the gate. The second one is also an arctan, but we're going to have to be a little bit algebraic or arithmetic. So we want it to be a +1 for it to be in that arctan form. So we're going to factor out a 2 in the denominator. So I'm factoring out 2 in the denominator. So we're left with that. Does anybody see what is going to go in those parentheses? Y over root 2. Yeah. Y over root 2. Let's analyze that a little more carefully because that's not completely obvious. So we're multiplying this by 2 over 2 so that this 2 and that 2 factors out to that. So we're left with a y squared over 2. And we want to write it as a square. We want to write it as a quantity squared. Right? That's always our goal, is to write it as a sum of squares or a difference of squares. And this is y divided by square root of 2, quantity squared. The 2 distributes to the y, giving y squared. The 2 distributes to the root 2, giving 2. So that's the trick. That's certainly a little bit tricky, not obvious. But once you see it, it should make sense. So this is minus 1/2. I'm going to leave space. Remind myself RCR, because that is not just y down there. If it's not just y, there's going to be an RCR. You could do the RCR right now if you wanted, but I usually just wait. So this is going to be arctangent. Y divided by the square root of 2. Integration constant out there. What's going to go in our RCR spot? Root 2. The derivative of in here is 1 over root 2. Divide by 1 over root 2 means multiply by root 2. And that will be our final answer. Dun, 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 dun. So that is RCR. And so we're saying to ourselves the derivative of this is 1 over root 2. Dividing by 1 over root 2 is multiplying by root 2. All right, let's take a break. Let's take a break. Go enjoy your homework, your worksheets, and if you have any free time, doing something else besides math. But not too much. Not too much besides math. Skiing and snowboarding should be good this weekend. All right, I will stick around.